Okay, so we're very, very happy to welcome Professor Jim Poole here tonight. He's a professor at the University of Oxford, where he's director of the Environmental Change Institute, professor of climate and economic risks. His research in the past has been mainly on coastal flooding, water scarcity, for which he's had a number of medals and awards. And probably of most interest here is that he's leader of the UK Infrastructure Transitions Research Consortium, which is taking a systems approach for looking at the UK's national infrastructure and how it might be improved in the future. And that's what he's going to be talking about tonight.
Brilliant. Thanks very much indeed, Paul, for that introduction, and thanks for the invitation to speak this evening. As the title suggests, I'm going to be talking about infrastructure and really the way in which we think about infrastructure in the long term, and leading on from that, some methodologies that we've developed for modelling and for planning infrastructure with a national perspective, so looking ahead long-term, broad scale in terms of what are the challenges that face infrastructure, and how do we use systems perspectives and models to plan for infrastructure in the future. By infrastructure, I mean energy, transport, water, waste, and digital communications. We might come back to some discussion as to the way in which we go about defining infrastructure. That's what I might describe as the definition by enumeration. There are some more fundamental properties which might help us with a more general definition, but that's what I'm talking about. And energy obviously is one entity on that list. Energy is what I guess brings most of you here this evening. But the emphasis really is upon interdependence between energy and other infrastructure networks. I don't think anything I say about energy in this talk is going to be particularly surprising to this audience. The talk really touches on a number of different perspectives on infrastructure. The first, a long-term planning perspective. The second, we turn to look at the hazards to infrastructure and the way in which we think about analysing risks and vulnerability as a basis for adaptation decisions. We then look at some of the feedbacks within, in particular, the economy and land use, which operate around infrastructure networks. And finally, I'll talk briefly about the tools which we're using to do this analysis, in particular, spatial databases and visualization tools. But to begin with, let me just provide a bit of a perspective on where we've come from in thinking about infrastructure and plotting really the remarkable rise of infrastructure up the political agenda, which was reinforced again last week in the autumn statement in terms of the amount of emphasis on infrastructure investment within the way in which government is thinking at the moment. It wasn't always thus. And the way in which I and colleagues involved in my consortium arrived at this really was through an interest in climate change, both from an adaptation and from a mitigation perspective. And it seemed to us that infrastructure was really rather fundamental and quite under-researched in that context. So infrastructure is one of the most important foci for adaptation decisions because it's long-lived, so it's going to have to inhabit a changing climate in the future, and it's of critical national importance. Infrastructure is fundamental with respect to mitigation, given the amount of emissions which are for which energy and transport infrastructure is responsible. So that's where, so we felt that there was something going on with respect to infrastructure, and this was maybe 6 or 7 years ago, but that there wasn't really the capacity to think through how one would implement radical change within infrastructure networks in the long term, step by step, starting with the legacy of assets which we have at the moment. Then at about the same time, 2009, the Council for Science and Technology came out with this report, which really began to put infrastructure on the national agenda and underlined the multiple roles of infrastructure within society and the economy, and that's picked up quite nicely in this quote here. So starting with reference to the role of infrastructure in terms of competitiveness, then a reference to the social role of infrastructure, and then a reference to the role of infrastructure in terms of mitigation. And since then, infrastructure has rapidly gone up the agenda. Infrastructure UK was created towards the end of the last government, and produced the National Infrastructure Plan. And subsequent versions of the NIP have become more and more specific about what the government's commitments are with respect to infrastructure provision. And also you will note the increasingly economic rhetoric around infrastructure and the role of infrastructure in the economy and competitiveness. So this is the 2011 NIP. Britain won't be able to compete unless we improve our infrastructure. This is the 2013 NIP. And just to skip ahead to complete the story, this is what came out last week with the autumn statement. And the same strong economic emphasis, interesting because unlike previous versions of the NIP, actually beginning to get a bit more specific in terms of understanding what exactly are the economic roles of infrastructure. There's a boosting productivity and competitiveness, so there's recognition of infrastructure as delivering factors of production, allowing businesses to grow, so recognizing that if there isn't sufficient infrastructure that might constrain production, enabling them to reach suppliers, so an obvious reference to connectivity, deepening labour and product markets, again reference to connectivity in particular with labour markets as well, and then collaborate and innovate and attract inward investment, so ideas around agglomeration coming through there too. So some increasingly nuanced understanding about what the economic role of infrastructure is. But in all of the versions of the NIP, and I bring out this quote here from 2013, there's this notion that it requires a long-term sustainable plan, which means taking a cross-cutting strategic approach. What you won't actually find in the NIP is what exactly that long-term plan is. Though there's more in the 2014 NIP in terms of pushing out the horizon, trying to get beyond the notion of the NIP being a list of projects into something which is strategic. But there's not, and we might argue when is a strategy not a strategy, but there's nothing in there as far as I'm concerned which you might say, well, this is a long-term vision and a set of actions or an adaptive set of alternative pathways which we can see step by step adopting, which would get us to something which might be recognizable as that vision. And I'll come back to that problem in a moment. But to continue the plot, Sir John Armitt was invited by the Labour Party to do a review of the way in which infrastructure is governed in this country, and came up with the notion of a National Infrastructure Commission, which would produce a long-term national infrastructure assessment. I'm not going to go into the governance implications of this. What I want to point to here is, once again, there is an implication in here that we need to develop long-term evidence about the performance of national infrastructure, alternative strategies for how we might provide a national infrastructure, and some way of planning, comparing, deciding what those strategies might be. So we have Sir John Armitt, we have Infrastructure UK pointing in this direction of the need for a strategic approach, but somehow that hasn't yet materialized. And my argument is that one of the reasons why it hasn't materialized is actually the process of putting together a long-term cross-sectoral plan for infrastructure provision and analysing that with respect to multiple metrics, and then reaching a point where one can decide on what the most appropriate strategies might be, is limited by our analytical capability. That actually that's too complex for the time being, and the tools don't exist to inform that type of long-term planning. So it's quite easy to write down that we might need to do it, but actually the tools up until now haven't really existed to enable us to do it, even if we wanted to. And that's where the consortium, which I lead, has sought to step in to develop a new generation of assessment models to enable the long-term analysis and planning of national infrastructure from a cross-sectoral perspective. We've been very much targeted on the UK and saying, well, how can we develop tools which can be used in the UK to enable this revolution in strategic planning? But by the way, we think this is quite interesting internationally, and experience has proved that to be true, given the amount of international interest there is in this work. Just a quick view of what the consortium is. We're funded by EPSRC, and we have a large number of partners in government and industry and 7 universities. The questions we're addressing, which is really the way in which this talk is structured, is one, the long-term planning problem, and we're thinking about, well, what's the capacity of infrastructure networks to deliver infrastructure services at the moment? How might that change in future? And how does that compare with demand for infrastructure services in future? So what might we need to do on the demand side, on the supply side, in order to enable sustainable infrastructure provision in the future? Secondly, looking at the downside, what are the ways in which these systems might fail? And so what we need to do to manage the risk of failure to a tolerable level. And then thirdly, looking at some of the interactions between infrastructure, the economy, and land use. And that's all being put together in order to answer the question, well, what should Britain do? Just, excuse me, I'm suffering with a cold here. And what we've done is put together a family of models to enable us to answer those questions. And so I'll use this structure to go through each of those questions. So first, looking at the strategies for long-term infrastructure provision. And the way in which we're putting this system concept and models together is to start with the drivers of demand for infrastructure services, with demography, with the economy, and then translate that into specific demands for different categories of infrastructure service, look at what the assets are and the capacity we have on the supply side, and then look at how those two things compare and develop metrics for performance. Let me just look at that from another perspective, which is this diagram here. So now I'm being explicit about, well, what are the main drivers of uncertainty in infrastructure demand going through into the future, and there are many of them, but the ones which cut across all infrastructure sectors are around population, economic growth, energy costs, and one might think of some kind of cuboid of possibilities within that future driver space, and we're sampling quite extensively, but here I've just taken 3 possible samples from that space of possible drivers of demand, low, medium and high growth scenarios. Then on the supply side, we're saying, well, what are the alternative strategies which we might have starting where we are with the infrastructure network and then pushing those into the future. And I'll come back to these, but this is around things like minimum intervention, doing as little as possible, long-term capacity expansion, doing lots on the supply side, increasing systems efficiency, which is doing a lot more on the demand side, system restructuring, which is more radical reconfiguration. And we evaluate the performance of each of these strategies with respect to all of the demand side metrics in order to come up with a multi-attribute description of performance going forward. And I'll come back to those metrics of performance. But to go step by step through that, we begin with a range of population projections, nationally, regionally, and actually going down to a local authority district level, which is what's being illustrated here, because we need that level of spatial resolution of population in order to know where the demand for infrastructure services is going to change in different parts of the country. We use the population projections in a regional economics model, which is done at Cambridge Econometrics. And so this shows different structures of the economy in our central, high and low scenarios. And then we begin to translate that into demand for infrastructure services. And this is the energy perspective. So this is electricity and gas. This is 2010. These are demand from different sectors of the economy. And here we're beginning to see some of our different supply and demand strategic combinations. This is the minimum policy intervention one, so this is as close as one can get to business as usual. This is local energy and biomass. This is electrification of heat and transport. And I mean, the answer, as you will know better than me, with electricity demand is that it could go up or it could go down. One of the interesting things around where electricity demand goes up is when one begins to get large penetration from transport into the mix, and increasing residential associated with electrification and heat and transport. Gas at the same time goes down in those scenarios. Then on the supply side, and this is using the CGen Plus model in Cardiff, we've looked at a very wide range of supply infrastructure investment strategies. This both looks spatially at where the power plants are going to go and looks at the grid and what investments will be required in the grid. Minimum policy intervention, this is energy generation in gigawatts. This is minimum policy intervention with a carbon floor price within it. This is the electrification of heat and transport demand side scenario with high CCS penetration. This is a high offshore, and you'll see a different axis on the offshore one in terms of in particular the level of offshore penetration. This is a high nuclear demand side. So we're beginning to understand what are the different ways in which one can match up on a range of timescales and spatially those different supply and demand trajectories. And this is how it then translates into infrastructure investment costs and carbon emissions. So these are the different components of cost. The dots are the emissions. I mean, one can read quite a lot into this. My taking of this actually is, provided we're in this family here, getting your emissions down is not a million miles from where you might, what it might cost you in any case, in particular if you're prepared to work hard on the demand side. But other people in the room might have other views on that. Moving on, we've developed, we started life with the DFT's national transport model, but found really that for these types of large-scale strategic interventions, it didn't do what we wanted, so we've developed a new, very kind of broad-scale strategic transport model, looking at where the transport growth is might be, given these different population projections and different projections with respect to modal choice and car usage. What does that mean in terms of ports and airports? And I'm moving quickly now from the water perspective, what's happening in terms of water availability. This comes from the climate change risk assessment projections of water surplus and deficit for different water company regions in the UK, and we have a national water resources allocation model which says where is the investment going to be needed in order to match up water availability with water demand. Let me do a quick detour, because I thought this would be interesting for this audience, onto cooling water. So this is an interesting interdependence. Municipal water supplies are the largest abstractor in this country, but cooling water is the second largest, and so there's obviously a series of trade-offs and potential tensions there. The headline is that with closing down of inland coal-fired plant and nuclear new build on the coast, the requirement for cooling water in freshwater sources, which is the important bit, currently 41% of thermoelectric cooling sources, that's going to go down. The interesting twist on that is if one begins to get large penetration of carbon capture and storage. So this is freshwater abstractions. That's how much water you take out of your water source. But most of that water goes back if you're using once-through cooling. So the important thing actually is the consumption, this bottom family. Those of you who do this type of modeling will recognize at least some of those labels across the top of different energy scenarios for the UK. And the wedge to look at is the freshwater consumption, and you can see, as I said, that for most of these the consumption is going to go down. The nuclear is on the coast, apart from if one begins to get a significant penetration of CCS. This is gas, this is coal, and with the large CCS scenarios, one begins to get, actually in the 2030s and onwards, the freshwater abstractions start ticking upwards. Some of that CCS could be on the coast, but some of it will be on inland waterways, for example, down the Trent and other rivers in West, in East and South Yorkshire. And so over here we see this is what's going on at the moment this is what happens without CCS, and this is the peak we begin to see in high CCS scenarios. And we've gone on to look at under what climate change scenarios, what scenarios of water availability might this begin to bite on the trend, what's the maximum amount of generation that you could put on the trend with a CCS interconnector, with a CO2 interconnector going down the trend. Let me skip back out though to the big picture, to these different portfolios or strategies of infrastructure which we've analysed going forward into the future. I've referred to these already. So the minimum intervention strategy is basically we continue to invest, but we're really doing as little as possible in terms of the level of infrastructure investment, and relatively little on the demand side as well. The capacity expansion strategy is basically throwing a lot of money at the supply side. The system efficient strategy is much more emphasis both on the demand side and on putting more efficient technologies within the existing infrastructure network. The system reconfiguration strategy is looking at ways in which we might be able to invest to actually shift the shape of the network. And we've analysed these with respect to 4 metrics for the time being. So one is service delivery. How much service is being delivered by the system in total? That might be, as it is here, megawatt hours per year of energy, megalitres per year of water, megalitres per year of wastewater treated, millions of vehicle kilometres per year, million tonnes of solid waste per year. So that's the first metric. The second is a capacity margin. So this is effectively how much more capacity do we have as a percentage of the overall demand. So how close to the limit are we pushing this system? That you might think of that as being a security of supply metric. The third is with respect to cumulative cost, and the fourth is with respect to carbon dioxide emissions. And I'm sorry, this is work in progress, so we're still trying to devise a way of putting all of these metrics together on one graph, which you can actually see and understand, but you'll observe we haven't quite got there yet. But at least you'll get the picture that we're looking in a multi-attribute way through time. So these are 2010, 2030s, 2050s of what's going on in these different strategies. And you can, I mean, the one thing you can see are the green lines up the top. So this is the overall service delivery and energy. The left-hand one is, this is pretty much what we expect from electricity. We could do a lot on the supply side, and that's the second one. Or if we begin to do more on the demand side, more in terms of system reconfiguration, we can get the service delivery down, we can maybe get the capacity margins up. This is the story with respect to cost and emissions. So this is the type of trajectory we're on. And if we don't pay very much attention to these systems, we'll see emissions going up. If we go down the capacity expansion route, the thing you see coming in very strongly here is investment in transportation. That if you're just doing stuff on the supply side in transport, pretty much you can spend as much as you like. And in that context, you also actually still have latent demand in the system. You can get the emissions down to some extent, and there's a high proportion of nuclear within this. But if you're not doing stuff on the demand side, it's very difficult to keep the emissions down. And then systems efficiency is costing less, but there is perhaps a limit to the extent to which we can deal with future pressures just from the efficiency perspective. New services and planning involves more investment, but enables us to adapt more flexibly for the future. So that just gives you a snapshot of the way in which we're thinking from a long-term planning perspective about infrastructure systems, and you'll sense that there are, we're admitting multiple alternative plans. We boiled that down just to 4 there, but actually you'll understand that there's a great deal more optionality underneath that. But we're beginning to get into a position where you can actually, on a timescale out to the 2050s and beyond, look across each of these infrastructure sectors, understand the interdependencies between them, the cross-sectoral demands, and use that to analyze how infrastructure is going to perform in the long term. The next perspective is then, okay, that's all well and good. We understand what the networks that we've got are, but how might these networks fail? How resilient are they, in particular in the context of a changing climate? And how might we use that information to target investments to reduce vulnerability within the network? And this again very much takes an interdependencies perspective. And the interdependencies here is what effect does interdependence have on failure and the potential for cascading failure. And we've put together a national infrastructure risk assessment model, which begins with a national perspective on extreme hazards, looks at the fragility of infrastructure assets in order to estimate the probability of failure, then cascades that failure through networks to understand the scale of customer disruption, and then propagates those customer disruptions through the economy using an input-output model in order to evaluate full losses. And then we can use that to trade off costs of adaptation with the benefits of risk reduction in order to come up with optimal adaptation decisions. So let's just step a little bit in a bit more detail through those things. It begins with mapping of the spatial extent of hazards, but we need to not only understand where the assets are that are exposed, but also we need to understand the spatial correlation between hazards, because we're trying to look at the whole country at the same time. And so the way in which we've approached this problem is very much the way in which the catastrophe modelers in the insurance industry also approach it, is by generating a large event set of possible spatial extreme events. So this is a large number of possible extreme rainfall events, and then propagating each of those extreme rainfall events through a rainfall runoff model in order to generate an event set of possible hazard footprints. Then going down to the failure mechanisms of individual assets. I mean, the engineers amongst you will know that, of course, there's a multitude of possible failure mechanisms, and in order to understand those failure mechanisms, you need a lot of very site-specific information. So we've looked at a relatively selective subset of failure mechanisms in order to populate this framework, but there's many careers of work for enthusiastic engineers to do to populate this framework with fragility curves for other failure mechanisms. Here we've done quite a bit of work on looking at the statistics of bridge scour and what the fragility of bridges is to extreme loading. What we've then done is connected all of the infrastructure together in interdependent network models, and this is something which has not existed in the past. You can get quite a lot of infrastructure point asset information, for example, in the points of interest data set from Ordnance Survey. You can get national grids, transmission and gas data, but you have to do a lot of work to snap all of that together into a coherent network model. And we've done that, and what's more, we've worked with the DNOs on the distribution layer to put together the first complete national hierarchy which goes through the different layers of transmission and distribution right down to the low level of distribution. We didn't have information from every DNO, so what we've done is statistically analyze the information we've got and synthesized plausible networks for the other DNOs. And then we can allocate customers to every substation within that electricity hierarchy. We've been working closely with National Grid on that. That works fine for the point assets, so electricity, water, telecoms base stations, wastewater treatment. You need to take a different approach for the transport assets, where you need to understand actually what the flows of passengers and vehicles on the network are. And interestingly enough, this information didn't actually exist, so we've had to use a lot of ticketing data and road survey data in order to construct this thing. And the first thing we did with this was something we were challenged by the Treasury to do, was to come up with a map of UK infrastructure hotspots. And by hotspot we mean a geographical location where there's a concentration of infrastructure assets which are critical in the sense that there's a large number of customers either directly or indirectly dependent on that asset. And so one can then map that geographically. We've done that for energy, water, waste, ICT. We've done it for transport. That's not very surprising. That just follows the road and rail network. And that's the Composite infrastructure hotspot map of England and Wales. Again, some of that is not very surprising. There's hotspots in large urban areas, but even that's interesting in that the hotspots tend to be around the periphery rather than in the middle of the urban areas. And there are a number of very interesting points which aren't urban areas in that map. Then that's an analysis of exposure in insurance industry terms. What one then needs to do is superimpose the hazard footprints in order to estimate what the risk is, and that's what this diagram depicts. Those are two hazard footprints, and one can then, this is a transmission network, you can then see how the failures cascade down through the different levels in the hierarchy of the transmission network. And actually we'd just done this last winter when, as you might recall, a flood began to materialize. And so we were asked to do this analysis going down the Thames Valley as the flood propagated down the Thames Valley, looking at the vulnerability of infrastructure assets. This is electricity, wastewater treatment, water, telecoms, airports, railways. Looking both at the direct number of customers dependent on those assets, but also what other infrastructures are dependent on the electricity, and so what might the effect of cascading failure be? How many customers are also indirectly dependent on those assets? And another thing you can do is then rank all of your assets according to that metric of dependency. So these are millions of customers. Up here, these are our most critical assets. And the numbers of customers, a fraction of that is actually the ones which are directly dependent on the electricity. A lot of that criticality comes through the interdependencies with other networks. The final part of the analysis is to say, well, given that we've got a particular scale of disruption, so many millions of customers disrupted, what effect does that have on business? How does it propagate through the economy, through supply chains? and this is the work which the team in Cambridge are doing using an input-output model, which gives you some measure of those indirect economic losses. So suppose that this is the direct loss here, and these are in millions of pounds per day. For this particular event, this then is the indirect loss, and that adds up to give the total loss. And in this case, the indirect loss is a bit more than half of the direct loss. Actually, as the direct loss goes up, the ratio of the indirect loss also goes up. So for very large events with large direct damages, you can have loss ratios maybe of up to about 2 or more relative to the scale of direct loss. So there's systemic risk going on there, in the sense that you have large damaging events, they scale up disproportionately in terms of their potential effect via supply chains on the economy as a whole. The if you look at those two perspectives I've just described, you might have the question in your mind, well, isn't all of that a bit feed forward? That you're, in the first part we were saying, well, let's look at demand for infrastructure services, the capacity of the infrastructure network, how do those things match up? How do we match up those things going forward in the future? And you might say, well, surely there's some feedback from the infrastructure we provide into the economy, into where people are living, and hence into the demand for infrastructure services. And that's absolutely right. So there is a dynamic going on there. And similarly, with respect to what I've just described around risk analysis, that's also quite feed forward. We're not really looking at the potential dynamics between, for example, catastrophic events and the way in which the economy or the way in which where people live might structurally change. And that's what we're trying to get our hands around in this third part of the research, which is looking at regional development and the way in which it is influenced by or adapted to infrastructure provision. And so that you don't need to look at the details of this, but what, I mean, this bit here you've kind of seen already, the demographics and the economics flowing into the infrastructure. What we're trying to pick up then is some of the feedback. So how does infrastructure, by providing connectivity, by promoting agglomeration, how does that make different places more attractive? How does that influence the out-migration rate? Also infrastructure by enabling efficiency and knowledge exchange, how does that influence the economy, and what influence might that have in employment on GBA and so on. So there's a much more kind of complex set of dynamics going on here, and I must admit that we're very much scratching the surface of this, but we are beginning to develop some dynamical models of regional development which incorporate infrastructure, in particular building on the new economic geography type models, which some of you may be familiar with, but extending those NEG models to explicitly incorporate the roles of infrastructure. So at least we're beginning to pin down, well, what are the different modes in which infrastructure does influence the economy via its influence on production costs, how much we pay for our electricity and water and so on, via potential limitations on factors of production. So if there's not enough water in a given region, then that's a constraint which will come to bear at some point, and we can't even buy our way out of that problem in the short term at least. What effect does infrastructure provision have on transportation costs, on accessibility to the workforce, on attractiveness of particular locations for the workforce, on promoting agglomeration and innovation. And actually, you might recognize some similarity between this list here and some of those words which I pulled out of the latest version of the National Infrastructure Plan, which demonstrates the thinking within Treasury around the economic roles of infrastructure. So with a couple of very simple models, one NEG model, one which is closer to a spatial interaction migration model, we began to play some tunes on those types of things. So these are looking at regional population projections in the UK, given different levels of connectivity, and those are GBA projections. Very much kind of proof of concept at the moment, but this is where we're going in terms of beginning to build some of the feedbacks in between infrastructure, the economy, and demand for infrastructure services. The final thing I want to touch on before I finish is some of you may be interested in some of the tools that are underpinning this. And we've built a national infrastructure database which hosts all of the layers of infrastructure data, but perhaps almost more importantly, also interfaces with all of the simulation models and hosts all of the data from the simulation run, so that we can then interrogate and visualize that data. So these are the various layers for the main infrastructure sectors for which we have large amounts of data. The hazard footprints, the population data, the economics data, and then some of the administrative and regional data. And that's all hosted within a geospatial database architecture, which enables us to pull out the networks and the data sets that we want and use that to parameterize models, push parameter sets out to the models which are held within the different partner institutions, push them back to the database, and then build visualizations on top of that. And so these are just some instances of the visualization tools. This is looking at the demographic data and population pyramids and what have you. This is looking at some of the network data, enabling us to pull out bits of that. And there are different versions of visualization, for example, using Sankey diagrams. This is looking at water abstractions for different energy generation sources in different parts of the country, which bits of that come from surface water and tidal water, and which bits of it go back to source or are evaporated away. So there's a kind of emerging suite of stuff there which we can use to really dig down into this understanding of what's going on with national infrastructure in this country. So I mean, this has been a hell of a ride, but where we're now getting to is this capacity to look from a long-term perspective at the performance of national infrastructure systems, to play out alternative scenarios for the way in which they behave, and to look at the risks of failure, looking across infrastructure sectors and at a national scale. And I mean, going back to where I started in terms of the gap, if you like, between the rhetoric of national infrastructure and what one actually needs to do in order to plan and deliver it, we're beginning to get into a position where we can actually build and analyze in a very specific way a long-term vision and strategy for national infrastructure provision. Then also look at the vulnerabilities and use that understanding of vulnerability to enable more targeted adaptation to risks. The final point here, which I haven't really emphasized up to now, but I hope it's been implicit somehow, is the large number of possible scenarios, hazards, demographic and economic projections that we're dealing with. So we're able to analyze performance across a very wide range of possible future conditions, and so try to identify strategies that are somehow robust in the sense that they perform acceptably well under a wide range of future conditions, and at least to understand sensitivity to some of the uncertainties in the environment and context which these systems will inhabit in future. So I hope that was of some interest, and I'd be very happy to answer any questions you may have on it.
Thank you very much, Jim. Fascinating journey through an awful lot of very high-impact research. We have some time, a little bit of time for some questions. If you'd like to ask a question, please put up your hand. Please tell us who you are and where you're from. And most importantly of all, please be brief so we can get as many questions in as possible.
Yes, I'm Neil Strachan from the UCL-Energy Institute. Jim, thank you for a most interesting presentation. Could you say something about how you're dealing with the issue of strategic versus incremental investment? Because there is a view that for infrastructures, these things come in large chunks, and politically and economically and socially for other reasons, you should just go off and do something. You should just go off and build very large infrastructures or commit to strategic investment. Could you just talk about that general issue and how you're looking at it from your modelling perspective?
And one can approach that problem from a optimization under uncertainty perspective. So what are the trade-offs there are that the large stuff, one might argue, gets you economies of scale, but you have to commit to it early in the face of a whole bunch of future uncertainties, and so you may have high regret in future if you make that commitment early. The incremental stuff, you can make more decisions as you go along, but there's a certain path dependency in that as well. And so within the energy supply and transmission modeling here, there is that multi-stage or full time profile optimization problem is implemented. And so one looks under a wide range of possible demand scenarios, what are the least cost options which are adopted, and then how do they perform under a wide range of alternative futures. And you begin to get some impression of what the trade-offs are. Are particular large upfront investments subject to that kind of potential stranded asset problem, for example, or are you better off making incremental investment? There's, however, I think an interesting point which is probably more debatable, which you were hinting at there, is there something more, a kind of je ne sais quoi, around the large investment commitment which somehow we don't pick up properly in that type of discounted through time optimization framework? There are arguments made about the infrastructure investments in the past, for example, by the Victorians under the sewer system, by the people who built Sydney Harbour Bridge, who built stuff which was massively over capacity, and somehow we're reaping the benefits of that now. And that type of investment would never have really made it through the type of optimization problem that I've just described, which is the way in which we're approaching it. And I think that there's an interesting question there about how we, well, it's in part to do with discounting, but how do we value the capacity, maybe the flexibility, which large infrastructure investments, maybe the opportunity which large investments might give us in the future. And I'd be interested actually in anyone's thoughts on how one might do that properly.
Hi, Amy Mount from Green Alliance. Thanks for a really informative talk. I had two questions, if I may. The first one was relating to that really fascinating map of infrastructure hotspots, and whether there might be reason in the future to include not just man-made, I guess, infrastructure like pylons and roads, but natural kind of assets like salt marshes, for example, which are incredibly important as a coastal defence against flooding. If we're using this kind of information as evidence to base the national infrastructure strategy, which will presumably direct investment in certain directions, and whether we should be thinking about investing in those natural resources as well as those more man-made ones. And the second question was, your research has been very, very spatially focused. How important do you think that national infrastructure planning, or maybe regional infrastructure planning, how important it is for that to be spatially minded and oriented?
Yeah, on the first of those, that takes us in a very interesting direction, which we haven't been through yet, which is around the extent to which ecosystem services certainly supplement or enable infrastructure service provision, and to some extent substitute for it. So say a salt marsh can or does at least reduce the wave heights of the sea wall. It might substitute altogether for the need for that built piece of infrastructure. And there are all sorts of other ecosystem services we can think of, for example, around purification of water, which substitutes for what has to be done in a water treatment works. And I think the capacity to evaluate that substitution of ecosystem services and compare it with the costs of doing the built infrastructure, there are a few interesting instances of that, but we can't do it systematically. And I think that's a real kind of gap. The National Ecosystem Assessment did some of that, but what I'd like to do is a much more kind of systematic analysis of the interplay between ecosystem services and the infrastructure services. And I think another way of approaching that problem would be via concepts of natural capital, in that what we've talked about here is built capital, but natural capital should somehow make it onto the same balance sheet. On spatiality, geography, well, I think it's absolutely fundamental, and so I think, for example, in relation to a lot of what goes on in the energy scenarios area, this is an energy audience, where I admitted that I don't think much of what we're doing is adding value to what's already been done, specifically in energy. I think we're adding value by understanding interdependencies. But the other area where I think we're adding value is by adding a lot of spatiality. And so on the demand side, for example, we're looking at very high spatial resolution about where energy demand is and where it might change in future. So, I mean, I think that's absolutely fundamental to the way in which we think about infrastructure.
There's a question, Mark.
Graham Stevens, bluegreenuk.com. You say it integrates all the disciplines and dimensions. Does that include regulations and legal aspects? So could you identify conflicts with EU directives and, or UK law?
Well, a part of this work which I haven't talked about at all, which has been led by Jim Watson's team in Spru in Sussex, has been looking at the governance arrangements for infrastructure, and in particular looking at interdependencies between infrastructure sectors and the extent to which they're enabled, or on the other hand there are barriers within the regulatory setup. And on the whole, the regulatory setups for our regulated utilities have been developed to some extent in isolation, albeit based on rather similar principles. And so it means that there are opportunities with respect to interdependence which have become very difficult to access because of regulatory constraints. An instance of that has been, for example, what the water utilities have and have not been able to do with respect to renewable energy, because Ofwat doesn't consider energy to be part of a water utilities regulated business, so they're free to do what they like with respect to on-site renewables or energy from waste, but it doesn't, they can't then try and recover the cost of that investment from their customers.
Gentleman
Niels Goldbeck from Imperial College. You mentioned that the resolution of your models goes up to the distribution level of some of the networks. So I imagine that there could be really interesting results also to look at for example, cities who want to improve their resilience. Has that been looked at? Could you say maybe a few words about this interaction between urban planning and national infrastructure planning?
Yeah, we've tended not to focus particularly specifically on cities, not least because of the amount of attention going on in cities in other areas, including presumably in your team at Imperial. So in a sense we've not focused on that. First, because, as I say, because it's a crowded space. Secondly, because, and I led the cities program within the Tyndall Centre a while back, and became frustrated by the boundary problem with cities, in that energy within cities comes in via transmission networks, water comes from the catchment, waste goes to incinerator somewhere else out in the sticks. And so from an infrastructure perspective, I found cities to be a rather frustrating unit of assessment.
I'm going to have to draw to a close there, I'm afraid.